In the second video, we're going to look at some basic aspects of the fragmentation reactions that are involved in mass spectrometry. The first thing that you need to understand is that what we're dealing with here are very high energy species. The way that we create the species that are detected is that first we have the neutral molecule. As we said before, we throw high energy electrons at it. This electron bounces up, but it expels one electron from the molecule so that we create two electrons. But the main thing is that we create the ionized molecule, which is a radical cation. This is a very, very unstable species. And what you want to understand is this here, this very, very unstable species, so that once it's generated, it's certainly not going to have a very long lifetime, but it's going to start breaking apart into all kinds of ways, some predictable, some not very predictable. And these fragments that we see on a mass spectrum. Now, beyond that, let's look at some of the aspects that are involved here. The example that we're going to be using is the spectrum that's right here. So it's the mass spectrum of octane, so 8 carbons. Let's look at some of the main features of this spectrum. We can see at 114 is the molecular ion, so just the ionized molecule itself. If we look further on the spectrum, the first significant fragment that we find is the one at 85. So if we look at the questions that are at the bottom of this slide, the question number 1 is what fragment corresponds to this this fragment at 85 that's observed on the spectrum. So the way that you want to deal with these is first know that you're not going to be able to identify all the different fragments on the spectrum, but then you just want to try your best at identifying some by looking at the masses that are involved. So if we look at what is involved going from 114 to 85, it shouldn't take you too much effort to figure out that there's a mass of 29 that's involved here. So what does that mass correspond to? And what is the ion at 85? That's what we're trying to answer here. Look at the molecule that's at the top here. It only has CH3s and CH2s. So you're trying to look at what could have been lost in this fragmentation reaction to form 85. So it's a loss of a mass of 29. Hopefully at some point you'll realize that you need to break some of the carbon-carbon bonds for this molecule to fall apart. And if you figure out that a methyl group, a CH3, is 15 mass units and a CH2 group is 14 mass units, then you can see that this 29 corresponds to the loss of a CH3 CH2 group. So loss of 29 units, right? So that question number 2, what did the molecular ion lose to form the fragment at 85? It's CH3 CH2. Now, if we're trying to answer the first question, then what fragment corresponds to MZ of 85? Well, it's the molecule of octane that has lost a CH3 CH2 group, and that has a positive charge. So it would look something like this. It's CH3 CH2 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 CH2, and there's a positive charge here on this last carbon. Because it is detected, you need to understand that this mass at this species at 85, it has to have a positive charge. Now let's think about question number 4 here, because it leads us to the important conclusion that's at the bottom of this slide. We know that the molecular ion at 114 has a positive charge, and then you lose something from that ion to form the other ion at 85 that also has a positive charge. So if something is charged, it loses a fragment and it forms a new charged species. What is the fragment that you lose? What is the charge of that fragment? It has to be a neutral fragment, right? So what we lost here, it's not a CH3 CH2 plus, it's not a CH3 CH2 minus, it's CH3 CH2 with an electron, which is a neutral species. So this leads us to this important conclusion at the bottom of the slide here. Because what we're observing on the spectrum are all charged species, and it's one species, charged species, that breaks down into other charged species, it means that what we're losing from one species to the other has got to be neutral fragments. that are not going to be detected on the spectrum. Let's look at some of the other questions on the next slide here. What fragment corresponds to the MZ of 71 on the spectrum below? Well, if you remember, we said that 114 leads us to 85 by the loss of 29, which is CH3, CH2. And then something that you can look at very briefly is that, oh, there is a difference of only 14 units here. And we know that 14 is a CH2 group, right? So what we know then is that the molecule that's at 71 here is the molecule of octane that has lost CH3, CH2, and a second CH2 also. And then you can see that to answer question 6, you can see that, oh, there's still another difference of 14 units here. So this is the molecule that has lost a further CH2 going on here. Now, questions 7 and 8 are what lead us to the important conclusion that's at the bottom of this slide here. And it's that although on the spectrum we can identify these parts so that it helps us to understand what's going on in terms of what is lost, what you really need to understand is that in mass spectrometry, a basic principle is that usually it's not a fragment of the original molecule that loses other fragments. It's usually always the molecular ion that loses fragments. So even though we can identify that between 85 and 71 there's a difference of 14, it's not the species at 85 that loses CH2 that forms the species at 71. It's the species that's at 114 that loses CH2, CH2, CH3 to get to 71. And it's not the species that's at 71 that goes to 57. It's the species at 114 that goes all the way to 57. So the important lesson that's right here is that on the spectrum, you can try to piece together what was lost by looking at small differences between peaks. But when you're thinking about what causes these different fragments, it's really always the molecular ion that fragments into different parts. So that if we go back to this spectrum and we look a bit at the fragments that are involved here, if we look at two of the important fragments that are on this spectrum, we have a fragment at 85, that's right here. We have a fragment at 29. What you need to understand is that these two have to be charged species because they are shown, they are visible on the mass spectrum, which means that they come from the loss of a neutral species, a radical. In the case of the fragment at 29, it would mean that we are detecting this carbocation here, and that the species that was lost was a radical with 6 carbons. In the case of the peak at 85, it means that we're actually observing the other side, which is that the positive charge ended up on the 6 carbons, and it's the radical here that was lost. Something that you might want to note here, we are dealing in mass spectrometry with very, very high energy species. So this is really the only time where you are actually going to see, and it's very, very common, actually going to see primary carbocations. So because we are in a very high energy environment, we are going to see these primary and even CH3 carbocations that we said in Chem 250 we were never going to be able to see in normal chemistry because they are too high in energy to obtain. So it's very common in mass spectrometry. Another thing that you'll want to remember is what's in the box at the bottom right of this slide here is that you're going to have to be able to work through a spectra by looking at some of the major peak and identifying what caused this fragmentation, so what was lost. So you'll want to remember the main fragments or tiny parts that can be lost that you can put together to try to get to different masses. Like we did before, we observed that there was a loss of 29, and we came to the conclusion and that must be the loss of a CH3 and a CH2 group. CH3 has a mass of 15, a CH2 group has a mass of 14. Well, those are definitely two of the most important masses that you want to remember, but you'll want also to remember everything that's in the table here. So CH2 has a mass of 14, CH3 has a mass of 15. When we have oxygens in the molecule, it's very common to lose the oxygen either in the form of an OH group that has a mass of 17. Very often we're going to lose an oxygen in the form of water, mass of 18. Sometimes we're going to lose a CO, the form of carbon monoxide, that has a mass of 28. And as we mentioned before in class, one very important signature by MS that you want to keep in mind is that an aromatic ring often shows up at 77. So remember these numbers, learn them. Then before we move on to looking at the mechanisms of fragmentation reactions, let's just look at the last important general aspect that we need to understand. First, remember what we said before, just keep that in mind, is that what we're dealing with here are very, very high energy intermediate, these radical cations, so that their chemistry is not always easy to predict. Sometimes they just fall apart in nondescript ways. So you should not expect to be able to explain all the peaks on a mass spectrum. That being said, for specific types of functional groups, there are typical reaction pathways for fragmentation that can be expected and that often lead us to be able to explain some of the major peaks on the mass spectrum. So that's what we're going to see in the next video. For now, let's just focus on our general fragmentation rule that's on this slide here. And it says this: whenever something fragments, we're going to form a carbocation, because that's what we detect on a mass spectrum of carbocations. Well, a very general rule that we can use that's very useful and that we're going to use in our mechanism is that the more the carbocation resulting from a fragmentation is stable, the more this fragmentation is likely to occur, which will translate into this next observation, that often the most intense peaks on a spectrum correspond to the most stable carbocations that we can form. So keep that in mind. We're dealing with carbocations. The more stable a carbocation is, the easier it is to form. So that just as a review, make sure that you remember this order of carbocation stability that we saw in Chem 250. We saw that the most stable carbocations are either tertiary or resonance stabilized. They have very, very similar reactivity. Then that adding alkyl groups onto a carbocation stabilizes that carbocation, which means that tertiary carbocations are more stable than secondary carbocations, which are more stable than primary carbocations, which are more stable than methyl carbocations.